1 and 2, but we ought to make a start because we have to kind of finish promptly at 4 o'clock so we can all rush across the other building for Steve Calley's talk. So it's a pleasure to welcome Steve Tobias on this second of our miniature intrusions into MHD. And actually, Steve suggested we should call this a Steve Fest. It's sort of Steve Bulbous yesterday, Steve Tobias today, and Steve Calley later. So Steve did his PhD with Nigel, I believe, in Cambridge, and then was lucky enough to get a fellowship at Trinity, a very rare thing to get, and then headed off for Colorado before returning to Leeds, where he's been for all 8 years.
Well, possibly. Well, thank you. I'm well aware I'm just a warm-up man, and I will try and get everybody across there for 4 o'clock. So I'd like to talk today about some work I've been doing with Fausto Cattaneo, who's known to many of you at the University of Chicago. And what we've been interested in is how turbulence can affect the dynamo, in what ways turbulence can affect dynamos. And in particular, we've been interested in coherent structures, which are ubiquitous in turbulence, and I believe are very important in dynamo theory. And I don't think they've been given the attention that they deserve. So I'm going to give them some attention and see what happens. Okay, so I'm well aware that some people in the audience are not dynamo theorists, and so I'll give some motivation and talk about the dynamo problem and what the equations and the parameters are. And then I'll talk about what I believe the outstanding problems in dynamo theory are that we're all trying to solve at the moment. And then I hope in the rest of the talk to give some ideas as to how understanding coherent structures in turbulent dynamos might help us with this. And then there'll be a little bit about what we actually did, some theory for how coherent structures might work in dynamos and a numerical example, and then we'll try and test the theory. Okay. Oh, I don't need to do that anymore. I've got one of these things.
There's a big stick in the corner.
A big stick, even better. Okay, I might use both. You're just out of reach, so it's not... Okay, so this is the standard motivation. Magnetic fields are ubiquitous in astrophysics and indeed in geophysics. And they really appear on a large range of spatial and temporal scales. And we're really trying to understand how these magnetic fields are generated. Today, I'm not really going to discuss the converse problem, which is how magnetic fields may act back on any turbulence that's there. That's a problem for another day. Next Tuesday, I might talk about that at the workshop that's here. So I'm really just going to be talking about the generation mechanism. And I've put here that these magnetic fields play a dynamic role in the evolution of all these astrophysical objects. And a fundamental question could just be then, where do these magnetic fields come from? And that's the dynamo problem. So here's the sun's magnetic field. I think every time I give a talk, no matter what it's on, I always have to show this movie because I think it's so cool. These are Galileo's sunspot drawings. And if you put them together, you get a nice movie of sunspots at the surface of the sun. And you can see that one of the key ingredients in the solar dynamo is rotation. Those sunspots are rotating with the solar plasma. And this is a more up-to-date version of Galileo's picture. This is a magnetogram of the surface of the sun. And you can see this large-scale magnetic field in the form of active regions, sunspot pairs, that's bubbling to the solar surface. And this is a systematic magnetic field, as we can see when we see the so-called butterfly diagram. This is the location of sunspots as a function of latitude and time. And you can see you get these waves, these large-scale waves of magnetic activity that migrate from mid-latitudes to the equator. And we believe that these sunspots, these magnetic fields, are generated by a dynamo. And you can see that this dynamo has nice and systematic properties. Oops. Okay, so we'll start with the equations. So for a turbulence workshop, I have no real need to introduce the top equation. This is just a Navier-Stokes equation. And the only extra term we have in here is from the fact that we're doing MHD, is the Lorentz force term. And this is quadratic in the magnetic field. J looks like curl of B. And so this is a quadratic force that's acting back on the fluid. And of course, in all of those astrophysical objects that I was talking about, we're usually at high Reynolds number. Okay, the Reynolds number is usually enormous, It varies from being enormous to being gigantically enormous. And so we're in a situation where we have turbulence. Okay, so we really want to understand dynamos in a turbulent medium, turbulent flow. And the other equation that we need to solve alongside the Navier-Stokes equations is the equation for the evolution of the magnetic field, which is a competition between advection, this is an advection term which leads to generation of magnetic field, and diffusion. And again, in astrophysical objects, we're usually in a regime where the magnetic Reynolds number is large, but actually not necessarily as large as the Reynolds number. Say for the Sun, the magnetic Reynolds number is large, but the Reynolds number is larger, and that's called the small magnetic Prandtl number regime. Okay, so we're really interested in solving this coupled set of equations, but that's not trivial to do. And so a lot of attention is focused on just solving this equation in isolation. You can see that if the magnetic field is small enough to start off with, this term being quadratic in B will have negligible effect on the turbulence or whatever flow you have. And you can think of an experiment where you start with a very small field and just solve the kinematic, what's called the kinematic the kinematic dynamo equation, where U is given or prescribed, or you can take it to be whatever you like, and then you just solve for B. Okay? This is a linear equation for B, and so you can get exponentially growing or exponentially decaying, or for particular value of Rm, marginal solutions to the induction equation. And actually today I am really just going to focus on solutions of this equation, although I'm going to choose for you, I'm going to choose some solutions of this equation or variants of this equation. But I'm not really going to focus at all on how the Lorentz force acts back. Okay, so I have some example parameter sets. This is for the Sun, just to give you an idea of how huge these numbers are. And just to focus on the base of the convection zone, say, the Reynolds number really is quite large. It's 10 to the 13, so we're fairly safe talking about turbulence. The magnetic Reynolds number is 10 to the 10, which is still large, but not as large as the Reynolds number. And that leads to this number here, the magnetic Prandtl number, to be quite small, 10 to the minus 3. Which we'll come back to a bit later on. Just for information, this is not a rapidly rotating, the Sun is not terribly rapidly rotating, although it is rotationally influenced. The Rossby number at the base of the convection zone is somewhere between 1/10 and 1. So we're not talking about a very rapid rotator, but these things are rotationally influenced. I keep doing that and I don't need to do it. Okay, so this is just my impression about what the outstanding problems in dynamo theory are, and I would say this really is the outstanding problem, and I'm not really going to address it today, but let's have a look. I would say, how does one get a systematic large-scale magnetic field? This is really an outstanding problem in astrophysical dynamo theory. I showed you that the Sun generates large-scale systematic magnetic fields as an 11-year solar cycle. But if one has a turbulent flow, which has energy on a wide range of scales, how can we possibly generate magnetic fields with a systematic behavior, the systematic behavior that we saw in the solar cycle? And of course, there's been an awful lot of work on trying to solve this problem. The most popular way of arguing this problem away is to say that there's an interaction of turbulent fields and flows in the presence of rotation, which somehow leads to correlations, small-scale correlations between the magnetic field and the flow, and that somehow gives systematic behavior. And this is all couched in this kinematic framework, so people really just looking at the induction equation in the famous mean field electrodynamics. Okay, so mean field electrodynamics really looks at correlations between turbulent flows and turbulent fields, if you like, to produce large-scale magnetic fields. Now, the mean field electrodynamics has run into a few problems recently because people have been doing numerical simulations and they don't seem to be able to find the correlations to be large enough, especially at high Rm, to produce systematic large-scale fields. So that's a problem. And it's the high Rm parameter that is the problem, because at high Rm, as I'll talk about later on, the dynamo really wants to generate small-scale magnetic fields rather than large-scale magnetic fields. So there have been a few modifications of this theory and competing theories. One nice idea that I think might be worth pursuing is that if you can't get enough correlations between driven convection and the fields that are generated by the driven convection, then you might look at flows which are driven by the magnetic fields themselves. So if you have a field and it's unstable to some instability, then that will drive a flow. It may be a turbulent flow. But that flow is certainly going to be correlated with the magnetic field that's driving it. And maybe that's a better way of producing correlations. So this is arguing that correlations may come through the momentum equation rather than through the induction equation, which is what's assumed for mean field electrodynamics.
Can you just remind us, this conclusion about small scales only, is that in the context of numerical experiments on homogeneous turbulence or triply periodic?
No, not necessarily. I mean, yes, there are simulations of, as you say, homogeneous isotropic turbulence in periodic boxes, and they show this. But spherical shells, simulations of convection in spherical shells also have this problem. Convection in boxes, they all have this problem. That at high RM, very high RM, you tend to generate small-scale fields rather than large-scale fields.
David Hughes, I don't think he's here, was
Yes.
telling me they've got one where they get a large-scale field. Are you going to tell us about it?
No, but I'll answer your question. They're not at very high RM. So that one is in the gap. Okay, because I know what David's talking about. That one is in the gap between. So the small-scale dynamo has not switched on, but there is a mean field effects. And then if you shear one of those, then at low RM, you can get large-scale fields.
I suspect also the Prandtl number is important as well, that you can have high RM, but if you have low Prandtl number, you can get large-scale fields even in high RM.
At low magnetic.
So the regime.
At low magnetic Prandtl number.
I'm sorry. Yes, magnetic.
That's a possibility, but I don't think it's been proven that that's the case because it's very hard.
It's been shown indisputably in many numerical simulations. I don't know what you call proof.
I would say at high RM. I would say at high RM.
Yeah.
No.
Several thousand. Is that high?
Sorry?
Several thousand for RM. Considered you consider.
Well, it depends how you define RM. But I would argue that there is no, convincing to me, demonstration of generation of a large-scale field. I mean, there are. Say for geodynamo simulations.
I get help on this from the numericists.
If you'd like to name a paper, I could. We could discuss it. But I would say.
Is it central to your main?
No, it's not central to my main theme. But I mean, I would be interested in any paper which shows at high RM. And the important thing is not really RM. It's RM minus the critical RM over the critical RM. That's the key thing. I mean, you could be at high RM, but if the critical RM is just one below it, then everybody gets large-scale fields. So I would argue that you're almost guaranteed to get be dominated by small-scale fields at high RM. And I would say at least 95% of simulations show that. Okay, but that's not really what I'm talking about. So anyway, I was just trying to outline the outstanding problems. Okay, another outstanding problem is what is the saturation mechanism for dynamos? So maybe I won't say very much about this because I'm not going to talk about this either, but just to give you a flavour. If you can find these velocity fields that lead to the growth of magnetic field, how does the dynamo saturate? And it seems to me that different dynamos saturate in different ways. The geodynamo simulations that we see, they saturate in a very, very different way to the turbulent simulations that we've seen trying to explain things like the solar dynamo. And there have been various mechanisms proposed that maybe the field reduces the flow to marginality. That's certainly not true for high magnetic Reynolds number dynamos. There's no way you can get everything to marginality. You could increase the dissipation, which is a possibility. And also there's been the suggestion that you might modify the Lagrangian properties of the flow. So there's various scenarios as well. But again, I'm not going to talk about that, so I don't want to. Okay. A final outstanding problem is this what's called the low PM problem, which has been alluded to. So given a turbulent velocity field at high Reynolds number, can this support growing magnetic fields if the magnetic Reynolds number is much less than the Reynolds number, i.e. if the magnetic Prandtl number is small? So as I was saying, in the sun, we're in kind of this region here, where nu is very much smaller than eta, so the Reynolds number is high, but the magnetic Reynolds number is not so high, but not so high. So we're kind of down in this region. The interstellar medium is somewhere up here, and numerical simulations are somewhere down here. So this is what we call, or Steve called, a high RM simulation at 10 to the 3, yeah? So simulations are down here, and the experiments are somewhere down here. So I think it's still fair to say I'm being very careful what I say here, because Steve's going to jump up in a minute. It's an open question as to whether this is, whether we can support growing magnetic fields at RM very much less than the Reynolds number. Okay, so in the language of spectra, this is what we mean by the magnetic Prandtl number being small. If one has the energy, the spectrum for the energy in the velocity field, and we have a spectral cutoff, Ku, then this is much higher for the velocity field than it would be for the magnetic field. Okay, that's what we're talking about when we're talking about the low Prandtl number regime. So the question is, can one generate a magnetic field in the inertial range of whatever turbulence is there? Okay.
Steve, just to give you some support on this, the critical magnetic Reynolds number for a small-scale dynamo at low magnetic Prandtl number
is enormous.
Is enormous.
Yes.
Right, several hundreds.
Yeah.
Maybe 600.
Yes.
So 1,000 actually isn't a very big magnetic Reynolds number.
No.
Oh, 2,000 starts to get big.
Well, I mean, of course it gets big, but the question is, can you...
It's compared to criticality.
Sorry?
It's compared to criticality.
Yeah.
I mean, it's compared to... The
Yeah,
problem.
compared to criticality.
So I think, Steve, if you're talking about the general simulation stuff,
You're
you're
talking
not
about
far.
Alex Checker-Chean's results?
No, well then, no, they're not large-scale dynamos. No.
Well, they're certainly dominated by the largest.
You're talking about the ones with
spectrum is
shears?
Dominated by,
The shear dynamo?
The shear ones.
well, there are
The ones in the kind of
those are
really
driven-
long,
I
thin
think
box.
Those are driven boxes.
Yeah. Okay, I would argue then they're nothing like at high RM. Okay.
As a co-author on that paper, they're nothing like it high R.
Okay. Okay. But okay, it's not really the point. Okay, so these outstanding problems in dynamo theory, I would like to ask: are there any generic answers to the problems posed? You know, is it model specific? Does it depend on what model of turbulence we take, or the nature of the turbulence? And to what extent can these be answered using the statistical techniques of turbulence? And the particular question I'd like to ask and answer is do coherent structures play a role? Can we answer some of these questions at least if coherent structures are present in the flow, and do they make a difference? So you could ask, coherent structures, are they beneficial or detrimental to dynamo action? And can we construct a theory for coherent structures in dynamo theory? So, well, this was for a general MHD audience. For you guys, coherent structures is kind of bread and butter, so you know all this stuff. Turbulence is a very hard problem because there's a superposition of the random elements and the coherent elements. But in geophysical and astrophysical fluids, the coherent structures are often very important. If you have stratification and rotation, that tends to lend itself naturally to the formation of coherent structures. And usually these are structures that contain the local helicity in the flow. They can be found on all scales. They usually take the form of vortices, but not always. And these vortices, they contain the non-trivial phase information about the turbulence, which I believe is very important for dynamos. I think you need to keep track of the phase information of turbulence. So here are some astrophysical, if you like, simulations of this one is the vortices that arise due to the nonlinear saturation of Rossby waves in an accretion disk simulation. This is a simulation of compressible convection. Actually, it's compressible penetrative convection, and the coherent structures you get there are downflow plumes, which tend to contain all the entropy in the flow. So this is highly stratified, and one tends to get very strong downflows and weaker upflows, and it's the downflows that take the form of kind of sinking plumes, which are vortex tubes. So this is the kind of thing I'm thinking about when I'm talking about coherent structures. Okay, so let's go back to this equation that I'm going to solve, the induction equation. And as I've said, and we've talked about, Rm is the non-dimensional measure of advection to stretching, and it's typically very large, which is good for dynamo action, okay? And I've non-dimensionalized the induction equation here in units of the turnover time. Shorter turnover times, in general, means better dynamos, okay? So if one has an eddy and it's going round very fast, then the magnetic field will be generated on a timescale that's associated with the turnover time of that eddy. So fast spinning dynamos are good dynamos, okay? So I'm going to be looking at how these dynamos work in a cascade of coherent structures, but we'll fix ideas by looking at flow on one scale, and then we'll just generalize up to more than one scale. So imagine one has a big eddy and a small eddy, okay? And one can say there's a turnover time, of course, associated with that eddy, which looks like a length scale over a velocity scale, and the magnetic Reynolds number that's associated with the eddy looks like a typical velocity times a typical length scale over eta, okay? So when one looks at a big eddy, then its magnetic Reynolds number associated with that big eddy is large, which is good for dynamo action, but also its turnover time is large. So that's a big and slow eddy, and that's bad for dynamo action, okay? This is good for dynamo action, and this is bad for dynamo action. Whereas for the small eddy, it's going around very fast, so the turnover time is small, which is good for dynamo action, but it's not at very high Rm, or it may not be at very high Rm. Certainly it's not at as high Rm as this one, and that's bad for dynamo action. And which one wins depends on the nature of your spectrum of coherent eddies, okay? So we have a competition between, is Rm large enough for dynamo action? If it is, then the ones which are fastest will win, okay? So if one has a dynamo on one scale, one is probably interested in its behavior at very high Rm, okay? And this is just a technical definition between a fast dynamo and a slow dynamo. For one scale eddies, then the field is definitely generated on scales smaller than the flow at high Rm. And if the growth rate remains finite as Rm tends to infinity, then we just call that dynamo fast, a fast dynamo, okay? So one could plot the growth rate as a function of Rm for one eddy, and it could look like this, in which case we would call it a fast dynamo, or it could look like this, in which case we'll call it a slow dynamo, okay? If the growth rate tends to be negative for the magnetic field as Rm tends to infinity. And you notice for both of these, Rm has to be large enough, go past some critical threshold for dynamo action to set in. If Rm is very small, then we don't get dynamo action whether it's fast or slow, okay? So one can imagine that the flow on one scale might have a growth curve that looks either like this or like this. And we're going to assume it looks kind of like this, because that's the generic thing for turbulence, for chaotic flows. If the flow is chaotic, it exhibits Lagrangian chaos, then the generic growth curve is something that looks like this. And we're going to assume that there is a growth curve that looks kind of like this for each scale of eddy in the turbulent cascade. Okay, I won't say anything about that. Okay, so what we're going to do is now look at the dynamo, having looked at one scale, we're just going to investigate the dynamo properties of a turbulent cascade of eddies at high Rm and Reynolds number, both analytically and numerically. Okay, so analytically we're just going to look at the superposition of these fast dynamos that we've talked about, and then we're going to do some wacky numerics to try and verify our theory.
The slide before.
This one? No. That one.
Yes. This is valid only at large magnetic Prandtl number?
Yeah.
You kind of slipped that in.
Yeah, I did. Yeah. Okay, I didn't really, because, okay. formally, when one talks about fast dynamo, what you do is you fix the flow and then let Rm tend to infinity. That's what a formal fast dynamo is. So once you fix the flow and you let Rm tend to infinity, you're implicitly assuming that Pm is large.
On the same order,
No, large.
larger than RM.
Rm is large compared with Re. So the magnetic Prandtl number is very large.
Compared with what?
1.
Oh, not necessarily RM.
No.
Okay.
No. Which
You
is
could have a definition in which you fix the Prandtl number and then...
yes, you could, but that's not what fast dynamo theorists do. I agree.
I agree.
Yeah. It's interesting because for years everybody, I was going around saying, we're interested in the fast dynamo problem. We're interested in the fast dynamo problem because look at the magnetic Reynolds number in the sun, it's huge. Yeah? But that doesn't really make any sense because the magnetic Prandtl number is small in the sun. So the technical fast dynamo problem, which people have been looking at for years, is not really relevant at all to the sun. It's relevant to the interstellar medium or somewhere where Rm is. Yeah. Okay, so let's try and fix some ideas, okay, which we've done. So we're going to consider a turbulent cascade of eddies with an energy spectrum looking like k to the minus p. And let's say each eddy in isolation, so let's choose an eddy in our cascade. Well, let's try and say something about its dynamo properties. So the large scale eddies are large and slow. So they have a large Rm and a long turnover time. So these ones might be good because they're at large Rm, but they're slow in the sense that they have a long turnover time. And these ones, the small scale eddies, they're small, so they're at low Rm, and they're quick in the sense that they have a short turnover time, and so they might be good if they're at an Rm high enough that they're above the critical Rm in the growth curve. So let's fix ideas and say if v of typical velocity looks like k to the minus alpha, okay, then Rm looks like k to the minus alpha plus 1, and the turnover time looks like this, okay. So if I pick an eddy in the middle, I can tell you what its Rm is and what its turnover time is, and therefore if I assume the growth rate curve to look like what I plotted, say something like that, then I can tell you exactly what the local growth rate is at that eddy. Okay, at that scale, because I know on my graph I know what Rm I'm at. Okay, I know that my growth frequency is measured in units of my turnover time. I know what my turnover time is, and so I can work out what are the active dynamo modes, which are the ones which have the highest local dynamo growth rate. So just plotting the figure, so if we have, I've just chosen an alpha here for 0.2, the velocity scaling like k to the minus alpha, Rm will scale like k to the minus alpha plus 1. My turnover time will look like this, so these are fast eddies, these are slower eddies, and my growth rate, my local growth rate, will have a distribution that looks like this, which is just got from plugging this and this into that curve. Okay? And we see that the dynamo scale that wins, the eddy scale that wins, is something in the middle. It's not the very big ones and it's not the very small ones. These ones don't win because they're very slow, and these ones don't win because they're at a Reynolds number, magnetic Reynolds number, which is below the critical magnetic Reynolds number for dynamo action. And so it's one in the middle that you might expect to be doing all the work.
But surely when you say the middle, the peak scales
With the outer Rm, it does.
Yes.
It does. And so as you increase Rm, this peak will move that way. That's true.
And it's close to the maximum unstable mode, right?
This peak is.
It's fairly steep on the right-hand side of that curve.
Yes. Yes. So it's those eddies which are just above marginal, which are of Rm, just above Rm crit, and are the fastest that win. But remember, where Rm crit and how fast they're going depends on the spectrum of your turbulence. Yeah.
So the peak scales are some.
It scales with alpha. Yeah.
Yeah.
That's
How
right.
did you calculate that sigma? You took some sort of turbulence model and somehow did a kinematic dynamo on it?
No, what I did was I assumed something, and what I assumed was this. Okay, so let me just, this is the growth rate measured in units of the local turnover time, okay? The turnover time scales like this. RM scales like this. So let me just take a point on this curve where k is equal to 10. So where k is equal to 10, I know that the magnetic Reynolds number is something, okay? Whatever it is. Looks a bit like 50 here. So 50, I go to my growth curve. 50 is a dynamo with a growth rate of something that I know, but I know that that's the growth rate measured in units of the local turnover time. So then I have to renormalize with the local turnover time.
That's from a model with one wave number of motion in it, is it?
That's exactly right. So we're assuming that there is no interaction between the modes, which is an assumption.
Right.
But if I have time, I'll come back to that assumption. Okay. Okay, so let's have a look at how well this theory does. So we're going to try and illustrate this via an example. And there's an infinite ways of trying to get a velocity field, which will illustrate what's going on. And so we did something a bit strange, I think. We know that magnetic fields generated by dynamo action have to be fully three-dimensional by Cowling's theorem. So we could just do a 3D numerical simulation of the Navier-Stokes equations, but in order to get some fairly believable results, we believe we might have to do a 4096 cubed calculation. So we're not going to do that. We're going to cheat. And we're going to use what we call a 2.5D velocity field, which has all three components. If we don't have all three components of the fluid velocity, then we know we can't have a dynamo either, okay? So I choose a velocity field which has all three components, but only depends on two of the components, okay? So this is U, but B now has this form, okay, where Kz is my wave number in the third direction, which is now enters into the problem as a parameter. So I choose a U of this form and a B of this form. Kz becomes a parameter, and I could now do a 2D calculation, okay? But the question is, how do we get U to get a realistic spectrum? Because we know if we just do 2D turbulence, we're going to get something that looks completely unrealistic. We're going to get, well, something that's completely not 3D, and I won't say about unrealistic. It's completely dominated by large scales, okay? So the question is, how do we evolve U? And this is where it starts to get very esoteric. We solve what are called the active scalar equations to get the velocity field. Okay, so these equations are probably well known to you guys, but not very well known in the MHD circuits, as it were. So these equations are, if one thinks of Q as the vorticity, okay, I solve the evolution equation for the vorticity, the usual Navier-Stokes type evolution equation in 2D, but instead of putting Q is minus del squared psi, which is what I would do for 2D turbulence, I have a parameter lambda, and I put Q is equal to minus grad to the lambda psi. So this is just a trick. I'm going to use this as a trick to do pseudo 3D dynamics in 2D, okay? And W I'm going to put equal to Q, okay? And I'm quite happy about doing this because W satisfies the same evolution equation as Q. Okay, so for lambda equals 2, these equations reduce to 2D Navier-Stokes equations, which everybody knows the dynamics of. There's an inverse cascade and we get large scales. But if lambda is less than 2, if this parameter lambda is less than 2, then we get what I'm going to call pseudo 3D dynamics. You do get a forward cascade you get local interactions and you get a forward cascade. And I'll show you some pretty pictures. For lambda equals 1, this reduces to something that, again, is probably well known to all of you, something called surface quasi-geostrophy. And all the simulations I'm going to show you are for either lambda equals 2 and lambda equals 1, but we have changed lambda between those things. So let me just show you, and because now we're going to do a 2D calculation, we can get interesting dynamics. So let me just show you what a calculation looks like. So these are you doing something like 4,096 squared calculations. And this is for lambda equals 1, I think, these calculations. And what we can see is we have this dynamics of vortex-vortex interactions, which vortices on quite a lot of scales here, vortices moving in the flow of other vortices. And you can see, hopefully you can see that the magnetic field is generated, well, kind of at the edges of certain vortices, okay? This is the X component of the magnetic field. This is very small scale, okay, very small scale magnetic field. So I'm not talking about the large scale field problem. And you can see from these movies that, say, this vortex here is generating a lot of magnetic field at the edge, okay? So what we're going to try and do is try and work out which vortices it is which is doing all the work. And do they relate to our dynamo scales that we worked out earlier?
What's the spectrum? The spectral slope for this one?
I didn't plant this question. Okay, I'll come to that in a minute, yeah. So this is just kind of changing lambda. We played around. So this is lambda equals 2, and you just end up with 2 large-scale vortices, which everybody knows, okay, with a forcing wave number of 4. This one's forced at a forcing wave number of 4 for lambda equals 1, the surface QG, and I'm sorry, the colours haven't come out very well, and this is what the final thing looks like. And this is forcing at a wave number of 100 for lambda equals 1. And you can see we get 2 big vortices and lots of technical terms crap in between, okay? And then you asked about the spectra. So these are the spectra. So this is spectrum of Q squared, Q. You might want to call it the entropy, but in surface QG it's not. It's whatever it is. I don't know what it's called actually. So here everything's on the large scale. For 2D Navier-Stokes there's a complete inverse cascade. For lambda equals 1 and for forcing at wave number 4, one has a nice forward cascade, and this is the spectrum, if that's of any use to man or beast, I don't know. There's some work by Peter Constantin and Ray Pierre Humbert where they try and work this thing out, but I'm not certain we get very good agreement. And this one is forced at wave number 100, and you get an inverse cascade and a forward cascade with different spectral slopes. And these are quite close to the theory, but
Cascade of what?
minus 2.79.
No, but cascade of what?
Oh, this is Q. But you have to be careful. That's not vorticity for lambda equals 1. It's what it. Yeah, it has the units of energy. That one has the units of energy.
Theory is minus 1/3 over
I thought you said this was entropy. Or
It's
surface
Q.
entropy.
It's this thing. It's this thing.
The square of that cube. Well, you could call
Yes.
it surface entropy then, I guess.
Okay.
Lambda equals 1.
Okay. I'm quite happy to call it.
I think of it as a delta function of potential vorticity.
So for lambda equals 2, I would think of these things as vortex tubes. Okay. Remember, we also have the third component W, right, which is coming out of the board. For lambda equals 1, I don't know how to think of these things except, But people who do surface QG know how to think about these things, but that's not me. I just do
Your
MHD.
W out of the screen has no role in the dynamics, does it?
No, so it's advected as a passive scalar. It has a role in the dynamics for the magnetic field, of course, because without W there is no magnetic field.
Only via the field.
But the field, the field is not acting back. So you can think of W as being a passive scalar, and B as being passive as well. So this is really, I'm just trying to get a velocity field which has coherent structures at all scales to shove into my induction equation and test this theory. I mean, other than doing a 3D calculation, this was the only way we could think of doing it. Yeah?
So if you assume long dipole too, do you still have growth of the length?
Yeah. So actually I looked at this problem with Stefan Llewellyn-Smith a few years ago for the case with lambda equals 2. So everything inverse cascades, you have large scale. You can still get growth of the field, they're excellent dynamos. But you can't answer anything about low magnetic Prandtl numbers because everything is on large scales. It's like, okay. So, okay, again, this is, maybe you cannot, maybe you can't see this, but see, this is the magnetic field. This is actually a close-up of one of those simulations you saw. And you see the magnetic field here is following a certain vortex. I don't know if you can see, there's a vortex there. It's moved round to there in the flow of this bigger vortex. And then it's moved round to here And you can see there's a very, very localized magnetic field that's being generated by this vortex and this vortex alone on that scale. Okay. So when one's talking about spectral quantities, that is not going to give a very good impression of this vortex whizzing round and generating a magnetic field. So I believe that spectra are only of limited use in analysing what a kinematic dynamo is doing.
What's the physical significance of the ratio Q over W? On the slide before, you had set Q equals to W.
Okay, so W is the flow out of the board, okay, out of the plane.
Oh, okay. That's
So-
a component of the velocity.
So if W is 0, then there's an anti-dynamo thing. So we need W to be some, but in 2D Navier-Stokes, W would satisfy the same equations as Q. It just gets advected round as a, so we may as well set it to be equal to Q. If it had the same initial conditions, it would be exactly the same.
But then you plotted the ratio of like of W over Q.
Did I? Sorry. Oh no, this is Q, sorry, Q or W, sorry.
Oh.
Sorry. I mean, because they look the same, right? So some people want to think of this as Q and some people think, sorry, better change that. Okay. Okay, so as I've put down here, it really is vortices of a certain size that seem to be doing all the work. Okay. And another close-up, a real close-up, here's that vortex that I was just poking out. I mean, this is a very high resolution. And this is the magnetic field around that vortex. So this is a vortex street in one of the other ones, and this is the magnetic field that gets generated by these vortices, which are of this size. Okay. So, as I put down, it's vortices all the way down. Okay, so what we did was we took one of these lambda equals 1 cases and plotted the growth rate against our other parameter kz, and we showed that this works very nicely as a fast dynamo. It works very nicely as a dynamo, and it looks like it has all the characteristics of a fast dynamo. But I'm just going to take one result here, and I'm going to try and test my theory. And the way I'm going to try and test my theory is to gradually take out scales from that simulation that I just showed you, from the velocity field, and try and keep track of the growth rate of the magnetic field, and then see if the growth rate changes significantly as I take out a certain scale of flow. So these are what we call filtered dynamos. So we solve these, what we call the pseudo 3D Navier-Stokes equations, and now we're going to filter the velocity fields. Now we could either cut off the large scales of the flow, cut off the small scales of the flow, and we do both. Now if we were clever, and freely admit we're not, and we knew something about wavelets, what we would really like to do is go into our calculation and take out that vortex and see if taking out that vortex dramatically changes the growth rate. But this is a spectral code, and that's not very easy to do because you have to keep track of where the vortex is. I mean, Marie-Fage could probably do this quite easily, but we couldn't. So what we're going to do is we're going to spectrally filter it. We're just going to take off wave numbers, certain wave numbers. And we're going to plot the growth rate and have a look at the form of the generated field. Okay. So we're nearly there. So this is what the velocity field looks like as one's taking out, say, starting from the large scales, okay? So this is the full velocity field, so we put the filter at k is equal to 0, and it looks like the full velocity field. If we take out the k equals 1 component, it looks like this, of the flow. Take out the k equals, all the way up to the k equals 10 component, it looks like this. And we take out up to the k equals 200 components, you could probably barely see that there are these ridges. So there is no large scale here, okay? So, but this, I mean, to be brutally honest, does not do such a good job at removing, say, a vortex. It doesn't do, but you can get a general idea as to what's going on. So the question is, what happens to the growth rate? So this is where we start off at k's, our filter is k fill. And this is where we're keeping all the modes. And now we start filtering off, for this one, the small scales. So we filter off up to k equals 500, and we get the result we get when we have all the all the modes, because the modes down from k equals 500 are not important in the dynamo process. As we go along, filtering and filtering and filtering, we get a small reduction in the growth rate, and then we get a massive dip in the growth rate, round about here. Okay, and what we say is once we take out the scale k is about 10 to 20, then the dynamo action seems to switch off. And as I've said down here, this is a pretty crude one. And going the other way, where we start taking out the large scales, again, this is on a different scale. For k fill is equal to 0, we get pretty much we get the growth rate we started off with. And we go along, and then we get a more gradual decrease. But again, the decrease starts to occur between 20 and 40. And you can do this trick for lots of different magnetic Reynolds numbers and lots of different forcing functions. And you can see there's some sort of usual k at which the dynamo switches off. Now this is an interesting one, because what we're doing here is we're actually moving the velocity from being at low magnetic Prandtl number to being at high magnetic Prandtl number. Because what we're doing is we have a cascade which looks like this, and our magnetic field is doing something, and it starts off doing something like this. We start off at low magnetic Prandtl number, and then we start off filtering the velocity field. So it starts to look more and more like this. So we're moving from being at low magnetic Prandtl number to being at high magnetic Prandtl number. Okay? Here the velocity cutoff, or though we've artificially cut it off, is at larger scale to the magnetic cutoff. And interestingly, as one goes from being at low magnetic Prandtl number to being, so the crossover happens somewhere over here, there doesn't seem to be any effect on the dynamo. It's only when you filter off the actual, what we call the dynamo scale, that the dynamo starts to switch off. So this would seem to indicate that there's no real intrinsic problem with a dynamo at low magnetic Prandtl number, providing you're at high enough RM, such that you have an active dynamo scale. So one could do the theory, because what we could do is we could measure the alpha, measure the slope of the spectrum, which is what we did, put it into a local growth rate curve, and plot the local growth rate and see how it does. And this is for different values of the overall magnetic Reynolds number. And what you can see is the local growth rate curve peaks at roughly this scale. I mean, it's not ideal. It's somewhere between 10 and 8 and 100, but it's not at 1,000. So we're kind of in the right ballpark at least. So why should we worry so much about coherent structures? Well, I believe that they can play a very important role in the dynamo process. And I think it's wrong to just talk about dynamos in terms of spectral quantities, which is what people want to do. And we did a kind of interesting experiment where we took one of these flows and then we randomized the phase. Okay, so we took this flow, which was the one I've just shown you, and then we got rid of all the phase information in the flow. So these two flows here have the same spectrum. Okay, they have exactly the same spectrum, but they have, as you might imagine, just looking at them, very different dynamo properties. Keep doing that. So this is the we get the movie again. This is the magnetic field. You tend to get a filamentary magnetic field with coherent structures, and you just tend to get a kind of random type of magnetic field when you've randomized the phase. This is like a salt and pepper type magnetic field. And here you have a different type of dissipation because you have long filaments of one side of magnetic field next to long filaments of the other type. And so this actually is a much, much better dynamo than this, despite the fact they have the same spectrum and they're at the same magnetic Reynolds number. So coherent structures are very important. And the reason is that it's the morphology of the field, of the resulting field, for the coherent case is very different. This one has much better folding, which is what you need to be a good dynamo, than this one. So I think spectral theories of dynamos are very limited, especially in geophysical or astrophysical situations where you do have a lot of coherent structures. I won't say too much about this, but one can have a look at large-scale shear flows as well. If you add a large-scale shear flow, which is something that people are doing to dynamos in convection or dynamos also with forcing. This is a very nice way of adding a large scale shear, because again you can get a very large separation between the shear size and the scale of the vortices. You can study the competition between the large scale shear and the small scale dynamo, which is generated by these kind of little eddies. This is a sheared type of calculation, and you can extend the theory to include looking at what the local Struhl number, which is the ratio of the shear stretching to a turnover time of the a shear time to the turnover time. And what you can do is you can calculate whether the local eddy, the local dynamo eddy that you've fingered as being the one responsible for doing all the work, what the local Struhl number is at that scale, and see if Rm is high enough, which we believe is true in astrophysical dynamos. If Rm is high enough, then the Struhl number will be small, and the small scale dynamo action will proceed largely unaffected directly by the shear, although it may be affected by the fact that the shear is affecting the larger scale eddies, which then cascades down. So this is I think is a nice tool for studying more difficult problems. Okay, so managed to get us here roughly on time. So I think turbulence is a lot more difficult than just the superposition of random waves. You have to take into account coherent structures. For dynamos in astrophysical and geophysical systems, the coherent bit might be more important than the random bit. For flows at low PM, well, I haven't said very much about this, but for flows at low PM, what you have to do is look at the active dynamo scale. And really, if that active dynamo scale is at an RM that's bigger than the RM crit, then it doesn't matter whether you're at high or low magnetic Prandtl number. So I would say, providing you're at high enough magnetic Reynolds number, you will get a dynamo even if you're at low magnetic Prandtl number, which is something the 3D calculations are starting to show, although it's very hard for them to get down to a magnetic Prandtl number of lower than, say, 30 or so, or 1 over 30. Oops, wrong way. There's competition between small fast eddies and large slow ones, and in general it's the ones that are pretty fast and pretty large, but not the largest ones and not the tiniest ones that win. And I've said this, there is no problem with having a dynamo at low PM. And this final point just comes back to Michael's question about, I was assuming everything was just on one scale, and then I assumed that the scales didn't really interact. So we did a whole other paper on looking at how much in the kinematic dynamo regime, if you have flows on different scales, how much can they interact? And they can interact actually surprisingly, well, I thought it was surprisingly a lot due to resonances that may occur. But in general, they don't interact too much. So that's, I believe that's not really too much of a problem. Okay, so I'll leave it there. Thank you.
One, Steve.
Yeah, he's going to set up.
Your sharp spectral filtering.
Yes. Yes, it was.
The Gaussian or.
No, it was just.
That didn't bother you. Gibbs phenomena.
We didn't get any Gibbs phenomena in the magnetic field equations because we're resolving the field all the way down. I mean, we really resolve so it's like, you know, you take a flow, you add a flow at the next scale. So we didn't get any sorts of Gibbs phenomena because we're resolving to a scale that's much smaller than the scale at which we're doing this spectral study. We solved the velocity field as before. Sorry, I should have made that clear. So the velocity field is solved exactly as before, and then all we do is we take a filtered version of the velocity field and shove it in the induction equation.
You filter it with a sharp spectral filter.
Yeah.
Something that
we
looks
take
like this could end up looking like a sausage. Because of the Gibbs phenomenon.
It can, but the magnetic field is very, very well resolved. I mean, if you have a look at I mean, we did lots of resolution checks, but if you have a look at let me just. So you're right. So when we take out the first 199 modes, we're left with this, which is a very, very small scale flow. But I mean, we're resolving down to K is 4096, so it still looks large. It still looks like a large scale flow from the point of view of our numerics.
I can't see that. What's it look like?
I know, it looks good on the screen.
I would
It looks-
expect it's like little strings.
Yeah, exactly. It's just like little worms.
Right.
Yeah.
Got your field there,
No, this is the flow. This is the flow.
the Q field.
Oops. Yeah, this is Q. Yeah.
I couldn't quite make out the magnetic field pictures. You had a grayscale plot of the X component of B, wasn't it?
Say,
I'm having
well, say
difficulty.
this one.
I imagine the lines are getting twisted around.
That's right. They're just getting wrapped around the vortex.
But is it
Right, so
like
this is-
it's just
Sorry.
light is
This one.
maximum one way and dark is
Yeah. So this is field pointing. Well, I don't know. Say to the right. So black is field pointing to the right. Strong field pointing to the right. So white is strong field pointing to the left. Okay. And grey, where is most of it, is weak field. Very weak field.
that black thing. It's probably some field lines more or less aligned that way, isn't it? It can't be.
Well, you have to be a
anything
bit careful because I haven't shown you what BY looks like or BZ. Okay, I'm just showing you one component of the
else.
field.
You don't have any field line pictures by any chance?
I don't, but I could easily make you some. But remember, the field is 3D. Okay, there is this BZ component.
But it's got to be solenoidal in a two-dimensional slice, doesn't it? It's got to be non-divergent.
No, because the field looks like
It can
it looks like
diverge
e
in
to
Z.
the ikz.
Oh, it can
Okay.
diverge in Z.
Yeah, so actually you never solve for BZ. BZ you just get from a divergence-free condition.
It's e to the ikz. Yes, you did say.
Yes. Yeah. Yes.
And
Sorry.
what do you do with your KZ parameter?
Well, we vary it to start off with to see how the growth rate changes as a function of kz. We know for kz equals 0, the growth rate must go to 0 because the field is going 2D. And then we just wanted to find some sort of typical behaviour, which we got. And this behaviour is very, if you look at, say, I don't know, the Galloway-Proctor flow or any of these 2.5D flows, they have this kind of typical behaviour of growth rate against kz. Once we decided that this one was an interesting one to look at, we fixed kz, and then we started filtering. So it may be that as we filtered, all these other ones changed as well, but we didn't, you know. These are still quite big calculations, even though they're not, even though they're 2D. Yeah?
And the kind of turbulence I know about, when you add some wave propagation mechanism, the coherent structures really take a hit. I mean, the fields look way less coherent.
Yeah.
Is that something that's of interest to you? I mean,
Well, I mean, in real turbulence, of course, we'd want to know what is the ratio of coherent structures to random element, and it probably varies from situation to situation. When we did, let's see if I can just quickly get this. I don't want to make people like. We actually took this velocity field here, which is from a 3D compressible convection, and did some dynamo experiments on it. And the dynamo was completely generated by these downflows. The field was, and that was what made us think that this was an interesting thing to look at. So for this convection, for this situation at least, the coherent structures were important, but for other, they might not be as important. Yeah.
Yes, there's a question in your last bullet, in the first bullet on your last slide,
The
where you
first bullet on the last slide.
mentioned spectral theories which are random in some way.
Right.
And right.
Oops.
And I'm a bit surprised that there are such theories proposed, because in general you can have a turbulence which cascades energy to one degree of scale size or another, and such theories don't need really what you would call coherent structures. They have to have a degree of self-advection. So if you have a self-advecting flow which is randomly interrupted in some way, that is the advection, then you would get a cascade as large or small scale, you would say. And it would not be exactly a turbulence. It would have measures of skewness and other things, which would be a kind of weak turbulence. And you would not necessarily see large or even small coherent structures.
Right. Right. I mean, I think I'm surprised that people have got so far using these kind of spectral theories for the magnetic field. That's the thing that kind of, you take a spectrum from your flow is given, and then
Are they really random waves without any nonlinearity whatsoever?
Well, the people just do the theory. They don't actually consider the situation. My own take was that you have to consider what situation the turbulence has arisen in to understand what the magnetic field that's going to be generated by that turbulence will look like. But the people who do the theories, they will just take a spectrum and they don't really think about where it's come from. And then they will make predictions about the magnetic field, the spectrum of the magnetic field.
I think at that point, actually, we ought to maybe stop because there's another seminar starting
In minus
3 minutes. Of course, we have-